Hello everyone, welcome to Pride, the new era of learning. This is Pack 365. In today's module 2, we're discussing about hill climbing technique through AI. So, let's begin the topic. Hill climbing is a widely used optimization algorithm in artificial intelligence AI that helps find the best possible solution to a given problem. As part of the local search algorithm family, it is often to apply to optimization problems where the goal is to identify the optimal solutions from a set of potential candidates. It is a hill climbing is a local search algorithm, right? We can assume here it is used in artificial intelligence widely and it optimization algorithm too. It is a part of local search algorithm. So, about the key points of the hill climbing. So here we have in the definition terms, we can read this. Hill climbing is a local search algorithm that aims to find the best solution to a problem by continuously moving in the direction of increasing evolution or values or decreasing the cost, right? It analogies to climbing the mountain, right? Continuously roll. So, we keep until going up to until you can view any higher. Hill climbing algorithm is a local search algorithm. Yes, it this means it explores the immediate neighborhood of the current solutions rather than looking at the other entire solution space, right? So, here we have the continuously move in the direction of the increases, right? Increasing evolution or a value. At the each step, it selects a neighbor state that improves the objective function. So it terminals when it reach a peak value or where no neighbor has higher value. So it terminates when it reaches the peak value. The algorithm stops when no neighboring state has the higher value than the current state. So this peak is local optimal. So we have it is a heuristic search technique. Yes, it is obviously heuristic technique. It is a part of it. So it uses the heuristic technique, an educated guess or rule of the thumbs. In previous lecture, we discussed about the heuristic search techniques and to guide this search rather than executing our systematic approaches. So it is also called as greedy local search, as it only looks to its good immediate neighbor state and not beyond that. It obviously it's called greedy because it is always make the choice that seems the best at the current moment without considering future consequences. It only looks at the immediate neighbors, direct transfer to the immediate neighbors. So, a node of hill climbing algorithm has two components, which are state and values. So here we can say each node or a state in the hill climbing algorithm has two main components. So what we have state and value, right? So for the state, the actual configuration, or we take a solution at the point, and for the value, the evaluated score or the object function value of the score we consider. So features of the hill climbing. So we have the features of hill climbing, generate and the test approaches. These features involves generating neighbor solutions and evaluating their effectiveness, always aiming for an upward move in the solution space. So hill climbing works by the generating neighbor solutions to the current state and the testing, evaluating it effectively. The goal is to always to move upwards in the solution space or meaning towards a better solutions. Okay. So another we have greedy local search. The algorithm uses a cheap strategy obtaining for immediate beneficial moves that promises local improvement. So as mentioned, it employ has a greedy strategy focusing on the immediate improvement. It makes moves that provides local benefits, hoping they lead to overall the best solutions. So no backtracking. Unlike other algorithms, hill climbing does not repeat other or reconsider previous decisions. Uh, presently, persistently moving forward in the quest of the optimal solution. We see the other uninformed technique use in AI algorithm, which we can see BFS and DFS. It may be DFS also IDDL DFS. So it may be backtrack, right? Once node visits the niche, it can be backtrack. But in hill climbing, there is once the destination is reached, so it does not consider any previous decisions or previous solutions. So we have different types of state space we can see. local maximum, global maximum, current state, float state. We have some kinds of state. Okay, so we can consume that. So here we can see here types of hill climbing. We have a types of hill climbing here. So we have a simple hill climbing, set hill climbing, and stochastic hill climbing. We discuss in forward. Let's start with simple hill climbing. Simple hill climbing is nothing but this is this version evaluates the neighbor solution and select the first one that improves the current state. For example, optimizing delivering routing routes might pick the first alternate routes that shorten delivery time, even if it's not optimal. Like we can consider as this is the most basic form, like it evaluates the neighbor states one by one and moves to the first neighbor that provides an improvement over the current state, right? It fast but might not be find a steepest ascent, right? So, is this some little bit? We can say that. So simple hill climbing. We have simple hill climbing. So here we have a step. So this type is more through it evaluate all the possible neighbor states and the chooses the neighbors that offer the greatest improvement, like ascent. Like okay. So algorithm steps for the steepest ascent hill climbing. So step one is evaluate the initial value, initial state. If it is the goal, return success. Otherwise, it has current state. Step two, check if the initial state is the goal. If so, return success and exit. So repeat until a solution is find or not. No further improvements is possible. Initialize it. So we have. So in step two, we can see like this. So if the initial best successor, if the no further improvements possible, initialize the best successor to be represent the best potential improvement over the current state, right? So we can say that for each possible operator which generates a neighbor, apply to its current state to get a new state. If the new state is their goal, return success, right? If the new state is better than the better successor, update. If the better successor to the new state, then can we keep it. After checking all the neighbors, if the best successor is an actual improvement over the current state, then we can consider it to current state is the best successor. So we have step three, enter a loop to search for a better state continuously. So here we have stop the algorithm. If no solution is found or no further improvements, right? If possible, mean the current state is local minimum. So here we have selection neighbors with a loop by applying the current state and evaluate the state. If it is possible, it return to success and exit. If it is better then can current state update. You have to current state to the this new state. If it's not better, it and continue the loop. So we have a final step here. End the process. If no better state is found, then the goal is not achieved. We can return the goal is not achieved. So no, here we have another steep hill climbing. It is designed to address one of the limitation of the simple hill climbing approaches. Because it designed to climb the simple hill approaches. So this variant accesses all the neighbor solutions, choosing the one of the most significant improvement in allocating resources in the instant. For instance, it evaluate all the possible distribution to the identify the most efficient one. So it actually we can see that if the best success rate will be considered, if it is existed, it can be do update, or if it not, it can be move with the best successor also. It during of the current state, right? So step and hill climbing algorithm. We have again here one algorithm. So we this also a one of algorithm of step at asset. So here I have evaluate the initial state. If the goal you can return success. Otherwise, set it as a current state. Repeat step two. Return until a solution is found or now no further improvement is possible. So in illustrate best, we discussed now initialize the best successor has the best potential improvement over the current state. For each operator, apply to the current state, then evaluate the new state, right? If the goal is return to success, we keep it. If the goal is return to success, if in case we can modify, other if it best, then better than best successor, update it or best successor to achieve the to this a new state. So if best successor is an improvement update, then current state. Like final step is to stop this algorithm. If no solution is found, further improvement we can print as a if possible. improvement is possible or achievement is not found. So now we come from the stochastic hill climbing. This is the version, right? So stochastic hill climbing does not look at all its neighboring nodes, right? So check if it is better than the current node. Instant, it randomly select one neighboring node, and based on the predefined criteria, it decides whether to go the neighbor node or select an alternate node. So overall the definition is to this version introduces a randomness instead of the always picking the best neighbor. It randomly select one of the neighbor that are better than the current state, right? So this can be sometimes helps escape minor local optima by taking a slightly less optimal but still improving the path. So we can see we have the diagram, state space diagram hill climbing. We have the diagram of this. So we can see here the state space diagram. Here we can see some features. Here objective function, global maximum, and a local maximum also we can see here, and the states of a shoulder for float maximum state. So here define this diagram. So let's start with the local maximum. So local maximum is nothing but this is a state that the supervisor has a higher value, right? So if it is a value of the supervisor has a higher value compared to all its immediate neighbors state, okay? But it is not the highest possible state in the entire problem space, right? Hill climbing often gets stuck here, right? Here get stuck. So it is a global maximum. This is the absolute best state in the entire problem space because its cost function of value is the highest amount of the possible states. It is the ultimate goal of the find this. Okay, it is the highest state of the graph. We can see the current state. Current state is nothing but this is a simply the state where the algorithms is currently located during its search. So we have flat local maximum. So flat local maximum is nothing but we called as plateau. These are the region where all the neighbor states have the same values as the current state. The algorithm finds its hand hard to determine which direction to move as there is no clear uphill like that. So we have the shoulder here. So mostly we called as a shoulder or shoulder region. So a region that appears the flat or like a local maximum, but it has an upward edges. So it has an edge, right? So we can say that edges, meaning those a path of higher ground, but it might be not immediately observe you. So this can also be a problem for the hill climbing. So when we get the short edge, we could not climb the hill, right? We could not reach our target. So the meaning behind it's saying like that. So it has a dimensional path. So here we can see different region. Like we all know, discuss now, local maximum, what is local maximum, global maximum, current maximum, flat local maximum. So same like that. I explain the graph. So now it is problem is different region in hill climbing. So local maximum. The algorithm terminates when the current node is local maximum has it better than the its neighbor. However, if existed a global maximum where objective found a value higher, so we already should implement in the image content, the algorithm gets stuck because any move always from the peak lead to a worse state, right? Because if you directly drop from the peak state, I do not means you're from falling the left, you're moving fast because it can be later worst decision or a better decision. So even if a higher global maximum existed elsewhere, because you are the if local maximum also existed a higher global maximum, right? Better than the local maximum. So the propagation mitigates the problem of the local maximum is to start exploring alternate path when it encounters the local maximum. Uh, so second we have ride. Uh, So right occurs when there are multiple. So here we can say right occurs when there are multiple peaks and all have the same values, or into other words, there are multiple local maxima which are the same global maxima. Right. We can see here. Right. A ridge occurs when there are multiple peaks, local maxima, that have the same value or where navigation requires a series of a moves that might not individually appear to the strictly up hills. So the image shows multiple peaks, which can also represent a complex landscape where the finding the true maximum is hard. Like the suggested solution is to move in survival directions. Simultaneously, we can say that which implies more search or parallel exploration. We can say that like this. So resist optical can be solved by moving in several directions at the same time. So here we have plateau. Plateau is a region where all the neighboring nodes is a region nodes all the neighbor nodes have the same values of the objective function. So the algorithm finds it hard to select the approximate direction, right? Approximate direction we found. So the flat region is where all the neighbors nodes have the same value. The objective function provides no clear direction for the algorithm to choose. Like solution of the plateau of one purpose of the solution is to take the big jump from the current state. This means making a larger non-local moves to hopefully land in the non-plateau region where we take clear guidance. So we have advantages of hill climbing here. So we can properly read here in this page. So advantages and disadvantages of hill climbing algorithm. So here we have simplicity. Simplicity is nothing but the algorithm is straightforward to understand and implement, right? So due to its individual nature. Memory efficient. It is a memory efficient, maintain only the current state data, right? So efficient because it only needs to store and process the data for the current state, and it is immediate neighbor. It does not need to keep track on the entire search history. So it is a memory efficiently. That's it. So we have rapid convergence. If it is often convergence fittily to a solution where the beneficial in the scenario where time is critical. So we can say it means the scenarios it converge quickly to a solution through often a local one, which is beneficial when the time is critical factors. Rapid conversion. So it disadvantages like suspicious. Its pronunciation maybe some critical. We have susceptibility to the local optimum. The algorithm becomes stuck locally. We can say that being because it only this is the most significant disadvantage. The algorithm can easily get stuck at a local maximum, believing it has a found the best solution when it much better the global optimum is existing elsewhere. So we have if we have a local variable, we also existed a global maximum, right? So this is one of the major minus point of the disadvantage. So limited exploration because it is the only consideration immediate neighbor. It has a very limited scope of the exploration, so this can be lead overlooking the globally optimal solution that requires the more through a temporary state, worst state. So we have a dependency and initial state also. So we can say that the quickly and efficiency of the solution found heavily depends on the starting point. So different initial may not be lead to the local optimum. So here we have applications like we have a marketing, we have robotics, and in job scheduling we use it. Right, for the in marketing, used by the marketing manager to craft the strategies. Instrument in solving classic traveling salesperson problem TSP by optimizing the sales routes and the reducing the travel time. This lead to the more efficiency for the sales operations and better resources utilization. Right, in robotics play a critical role in enhancing the performing and coordinating a various robotic components and contribute to the more sophisticated and efficiently robotic system capable of the performing complex tasks as planning, monitoring, more and control jobs scheduling. So here we have the within the computing system, it is a key in optimizing the allocation of the system, right? So the jobs across the different nodes. So we get the different of ensure that the optimal computation research. So overall the system is efficiently. So I hope you guys you all are done with this topic. I hope you all of you understand about the what is hill climbing. So we meet in next lecture. Until that, thank you.